Hey, good morning, everyone. I am Adrien. I'm the lead core developer on Arnold, and I've been involved in the Arnold GPU project since the beginning. And today I'm going to talk to you about what is new with Arnold GPU. So Arnold is, as you probably already know, a high-quality production renderer for visual effect and film animation. It's used by many studios, hundreds of studios on countless productions. And Arnold was instrumental in the shift toward physically based light transfer simulation in production rendering, a role that was recognized by an Academy Award. And Arnold is available as a standalone renderer and inside Maya, 3ds Max, and other third-party DCCs like Houdini, Cinema 4D, Katana. And today I'm going to also announce that we'll be releasing Arnold 5.4 tomorrow. Arnold 5.4 contains tons of new features like CSG shaders, improvements, and also newly supported features for the GPU beta, which is what I'm going to talk about right now. So Arnold GPU is in public beta. If you're using Arnold right now, if you download Arnold, you have access to the GPU renderer. So Arnold's been a CPU production renderer for 20 years. So why did we went for GPU? The first thing is that workflows are moving towards more and more real-time and interactive look development, lighting. People want to do things in a viewport and want to do things as fast as possible. Another reason for us to go towards GPU is that everybody has been asking for it for the past 5 years, and we listen to our users. GPUs are getting bigger. If you go for the top of the line with 2 RTX 8000, you have access to 96 gig of VRAM, and this is starting to look good for production rendering. And another thing is that for small and medium facilities, scaling using GPUs can be easier because the space it takes, the energy, it can be good. So when we set out to build a GPU renderer, those are the strict set of goals that we put on ourselves. First thing is we wanted to have a single renderer, not Arnold GPU, Arnold CPU. You're using Arnold, and the GPU renderer has to be feature compatible, which means that we want to support everything. Pixel compatible, we want a good match between GPU and CPU, and API compatible. If you build tools around Arnold, those have to run on the CPU and the GPU. And this is what we mean by a single renderer. The only thing you would have to do if you're an Arnold user, an artist, and you want to use a GPU is tick that checkbox. And like if you're going to use the same shaders, the same scene, the same everything, the only thing to do is to have a GPU in your box and tick that checkbox. And we want to have that in all the DCCs we support. And this is currently shipping. It's been shipping since March. And whether it's Maya, 3ds Max, Houdini, Cinema 4D, and so on, like all the DCCs. I'm missing Katana on the slide, but it's the same in Katana, same checkbox. So single renderer, that's the first and main goal and the main philosophy behind the project. So we want a renderer that is feature compatible. We don't want a preview renderer. We don't want something that you're going to discard. We want to aim for a final frame renderer. And to have a final frame GPU renderer, we want to support all the features. Now, some features are hard to do on the GPU. It's going to take some time. Arnold is super flexible, super customizable. And first, we decided to focus on the feature set that enables you to do character look dev, because incidentally, that's also the kind of asset that is going to fit on your GPU, at least at first. Eventually, we will support everything. The first thing we set out to support is the arbitrary shading networks that you know and love to use in Arnold. Like artists will build those very flexible and crazy shading networks. This is a shading network that is being used on that robot. And this has been running on the GPU since the first beta we released. We support nearly, like probably 85% of the shaders. All those things are running interactively on the GPU. And the first thing I want to announce in the Arnold 5.4 that we are going to release tomorrow is we also support OSL. So if you've been writing shaders in OSL, you can now run them on the GPU. a few things are missing. They'll be coming soon. And this is a partnership with the OSL development team, NVIDIA. And yeah, this is shipping soon. So with those sharing networks support, we can start and move to more complex scenes. And in terms of feature set for character look dev, yeah, those scenes speak for themselves. So this scene is rendering on an RTX 6000. Of course, this is not real time. This scene is extremely heavy. So you can see that hair is supported, subsurface scattering is supported, the hard surface integrator is working, lighting is working, and this is a very good match between CPU and GPU. In Arnold 5.4, we're introducing support for the new random walk SSS, which is an improved subsurface scattering mode that was added in Arnold 5.3. This is now supported on the GPU, as you can see, with good speed. We also improved the coverage of our own Uber shader, the standard surface material. Now everything is supported from transmission scattering, dispersion. We have a very, very good match between CPU and GPU. When we released, we were supporting atmospheric rendering. And the next thing I'm going to announce for Arnold 5.4 on the GPU is we're introducing initial OpenVDB support. So this is this is not going to work as well as on CPU, at least on the first. It's an initial implementation. It's likely to require more memory, but it is there, and it will be shipping tomorrow. And we're also adding volume displacement. And as you can see, good match between CPU and GPU. So one thing that was super important for us is that the scene is being shared by the CPU and the GPU. So anything you've put in your scene, whether it's procedural, instances, operators, which we will talk in depth at a talk tomorrow, I think, everything is supported from the start. And if you don't use the GPU, it's fine. No, there's no overhead. But if you do use the GPU, you can switch between devices live. And we will support the scene complexity that Arnold's CPU supports. So instancing works perfectly well. And we even support more pro-oriented features like light path expressions for AOV, if you can do heavy compositing with Arnold GPU, and this has been supported since the first beta. And so this is something new. This is something that we won't ship tomorrow because this requires new and experimental NVIDIA drivers. But we are going to add on-demand texture loading to Arnold GPU very, very soon. I'm talking weeks. And this is the initial results. Again, first an initial implementation, it will get better, but this already gets us through the door. You can see that on that scene requires 17 gigs of GPU memory, so this doesn't run on a 2080, for example. With on-demand texture loading, the first initial implementation that we have, this runs on a 2080. And this is, I'm not going to go over all the features that we're adding for Arnold 5.4 because I have a limited amount of time, but this is kind of our progress report for the number of features that we're supporting, and things have been increasing quickly. We've been releasing every month, we're releasing betas every 2 weeks, and every day we add new features, new shaders, new lights, and we're going to eventually go to 100% compatibility. The next goal for us, first one was feature compatibility, the next one is pixel compatibility. So what does it mean? We want a good match between CPU and GPU. And we set out those pixel compatibility goals. The first one is good enough for look dev, meaning that you're doing look dev on the GPU, on your machine. And once you like the results, you're confident enough in the renderer so that you can kick that to the render farm and get an image that matches what you were setting on your machine. So that's the first goal, and that was the first goal for the beta, and we're there, as you can see from the previous pictures. Then what we want to have is you kick one shot on a GPU, one shot on a CPU, you can use those in the same production. We want to get there in terms of pixel compatibility level. And eventually, the holy grail is to use a device per frame and then use both CPU and GPU on the same frame. And we'll get there, but we really wanted to get something that is already useful to all our users. There'll be some performance trade-offs and things that we need to figure out, but that's the end goal. The end goal is hybrid rendering. And as a kind of a progress update, you can see that match between CPU and GPU is good and is getting better. Our motion blur between CPU and GPU matches perfectly at the pixel level. Like you could use those two alpha passes as a compositing mask on a CPU and a GPU render, and it will work. The sampling patterns, the high-quality sampling patterns in Arnold are the same on GPU and CPU. The light samplers, the very high-quality light samplers in Arnold are the same on GPU and CPU. The shading matches very, very well. SSS on character, this is cloth for product design. If you didn't have the CPU and GPU markers at the bottom, you wouldn't know which one has been rendered on which. Just one was faster, that's it. Those are results made by our users on the beta forum. Again, good match. And this is the new and improved random walk. I can see all the nice details in the teeth, and this is working perfectly on CPU and GPU. So that's kind of the progress update for where we are in terms of pixel compatibility. Now, the next thing is API compatibility, which is harder to explain. But Arnold, what made the success about Arnold is that it's not a black box. Arnold is a rendering library that people have used to build tools, like renderers, plugins, look dev kits. That's the API we use as well for our integration in Maya, 3ds Max, in all the DCCs. And we really didn't want people to have to rebuild their tools when we switched to GPU. And we did that. If you've built a tool on top of Arnold, like for example, there's a third-party tool that we don't work on, which is called Gaffer. Gaffer uses Arnold. Gaffer was able to use Arnold GPU from day one because we were API compatible. So you can build tools around Arnold, but you can also build tools inside Arnold. You can build procedurals, you can build shaders, you can build cameras. And if you're writing those tools, you should be able to use the same exact API whether it's rendering on the GPU and CPU. And that is something we've been working on, and it's something we use internally. We haven't released that because we really want to make sure that it's good before we release it, because we don't want you guys to do work for nothing. But we do use it internally, and it will get there eventually. So Arnold GPU is in public beta, and we do improve it at every release, and if you want to get into the private beta program, we will release a private beta every 2 weeks. And please, if you use it, give us feedback, send us images. We're super happy to help debug and just to know it works. Arnold GPU runs only on NVIDIA GPU. I want to make that very clear from the start because it's built on NVIDIA technologies. And it supports from the Maxwell architecture to the new and fancy Turing GPUs. It runs on quad-range GeForces, multi-GPU is supported, and the link is supported. What you need to do is use the recommended driver, or a supported GPU, and you're good to go. So how did we achieve Arnold GPU? We achieved Arnold GPU by building it on top of technology from NVIDIA called OptiX. And we benefited from NVIDIA expertise, and we set out to improve OptiX to make it suitable for production rendering with them. And we've been extremely happy with our work relationship with NVIDIA. And some of the new production-oriented features in OptiX. And the biggest one, of course, which is something that's been in our heads since the beginning of the project, is that OptiX brought us RTX support from day one, or really day minus 14. and with that, I'm not going to talk about RTX because we have in the room the best man to talk about RTX in the world, which is Steve Parker, the architect behind the RTX project. So let's all welcome Steve Parker for the next part of the presentation.
So I'm going to give you a little bit of the story behind some of this. There's a lot of very cool stuff that Adrien and team have been working on, but you may not all know where it came from. So there's a handful of us that have been working on ray tracing for a long time, and these are some of the seminal works that I think of when I think of the foundation of that. Turner Whitted's paper we reconstructed physically at SIGGRAPH last year, if you were here to enjoy that. Followed by work on both global illumination at Cornell and distributed ray tracing by Cook and others, and ultimately kind of culminating in Jim Kajia's '86 paper, and that described path tracing and the rendering equation, and there's it's kind of inspired a whole bunch of people to go and figure that out, and how to make it work for production, how to make it work in real time. Well, there was an old joke. We can't actually find the origin of this joke, but ray tracing is the technology of the future, and it always will be. We're going to obsolete that one here shortly, but around that same time frame, just a couple years before this, I'd met Marcos Fajardo, and I was a professor at the University of Utah, and he was trying to figure out how to make ray tracing work for production assets, and how to make Arnold scale, and they had just released their first movie using it, and it's really inspired a lot of other people, and it's amazing to see now where it's come, and the progress both in terms of capabilities as well as performance over that time frame. And around that same time frame is when I actually joined NVIDIA, and NVIDIA was starting a ray tracing group, and we showed some very crude real-time things, especially compared to what we're seeing today, but we were really trying to figure out how could we make this work in real time. And we had performance of like 100 million-ish rays per second on a high-end GPU, but we thought, it's not really good enough. And how are we gonna get there? And when we looked at it, what we knew is that GPUs are, they're really good at shading, right? They're called shader cores for a reason, right? That's the streaming multiprocessor shader cores. That's all what the GPU is about. But it turns out there's other things that we're kind of missing. One is acceleration structures. How are we going to build acceleration structures fast enough for real time, or how are we going to build them in parallel so that we're not just spending all of our time building some acceleration structures and then rendering it really quickly? How would we go about doing that? Another big piece to the puzzle is denoising, and our AI denoiser, which we released a few years ago, is working in Arnold as one of the main pillars of that strategy, because you don't want to necessarily just brute force your way through it. That's not, let's be smart about it, and what better way to be smart than with AI? And then, of course, the ray tracing part of it. How do you traverse a scene? How do you intersect with triangles and so forth? And so that ray tracing is kind of in any render, kind of the main building block, and it's usually one of the big performance bottlenecks. And so the question is, how do you find what triangle in a huge data set is the one that hits a certain photon that you're simulating? And to the computer, it doesn't really look like a bunny. It's just a bunch of numbers. And so what most renderers have kind of converged to is something called a bounding volume hierarchy. The bounding volume hierarchy is where you have a box that contains some subset of the geometry, and if a ray intersects that box, you open the box and find several other boxes that contain some other subset, and you open that box and eventually you'll find a set of triangles, and you can quickly figure out what ray that triangle what triangle that ray interacts with. And prior to RTX, we developed kernels and algorithms that would try to do this as efficiently as possible on those shader cores. And the challenge with that is that the shader cores, then couldn't do shading while that process was happening. And we were actually pretty good at it. We could have continued doing that, but we felt like something that we needed to take a bigger step. That just waiting for process improvements and Moore's law and things like that, that was a little too boring. We wanted to really take a huge step forward and figure out how to make it have a step change in performance. So number one for real time, and number two for interactive use cases, like a lot of you on a day-to-day basis, and number three for improving or reducing the cost of offline production rendering. And at SIGGRAPH last year, probably many of you were there, we announced the world's first ray tracing GPU. Had a huge event, kind of bombarded SIGGRAPH with this big historic milestone in the evolution of ray tracing and in the evolution of NVIDIA. And interestingly, it's actually the first time we've ever launched architecture at SIGGRAPH. But we thought it was something that was really focused at the professionals that are building content all day long, and we really wanted it to be something special for this audience, and so we reserved it for SIGGRAPH, when usually would launch it at other places and times. So that Turing GPU has been described elsewhere, but it's actually a really big change, and it's not just the ray tracing cores. We also have tensor cores that bring artificial intelligence to mainstream GPUs, as well as increases in memory bandwidth and memory capacity, NVLink, so you can connect more than one GPU to scale up to 96 gigabytes of memory, and just a litany of performance improvements that make it better at ray tracing type workloads. So if we reflect back on that picture, the three buckets on the left that we had to work on algorithmically for the last 10 years, those are what the Turing SM is designed for, and what it's an excellent workhorse for normal graphics workloads, but it's also been expanded to ray tracing. And then the ray tracing cores do the traversal and intersection kind of heavy lifting. Previously was a whole bunch of instructions in order to test those bounding boxes for every single ray. We now have a dedicated processing unit that we call RT cores that offload that algorithm and provides a huge speed up for traversal and intersection, but it also allows the shader cores to continue working on other rays to shade those operations, to shade them and sample them and compute all of the material properties and other things that Adrien just showed. So, and the result was roughly an order of magnitude speed up in the overall ray tracing rate. And when you put it in the mix with other things, sometimes it's less, but it's really showing where we're trying to go with ray tracing performance. Fast forward a year later, well, RTX is everywhere. And here at SIGGRAPH, we're showing lots of things, adoption across a lot of industries, whether you're producing content for M&E or commercials or things like that. Arnold is is very pervasive in those industries. We have RTX in laptops that we're showing, as well as research showing off some of the real-time ray tracing and celebrating the anniversary of the moon landing. And it's kind of the new standard. So whether it's in gaming or architecture or M&E or designing products or even workloads you might not traditionally think of with high-end computer graphics, but we use in biology research and physics simulation. And so I'm here to claim that the future is here, so I think David Kirk's recitation of the joke is no longer valid, and I propose a new one. Maybe some of you have something that's more snarky, but I actually have students that have written path tracers and put it on the back of their business cards. But a lot of the a lot of us in the industry, and whether it's Adrien or Marcos or myself, that we've been in this working on chipping away at this problem for a long time. And so it's ironic that I have a student that can put a path tracer on his business card, and yet Adrian's here showing you all the things he's done with it over the last year. And so there's this duality that it's simple enough to fit on a business card and yet complex enough to consume an entire career, and probably many more careers to come. So that's a little bit about where it came from. And so how do you access those ray tracing cores? Well, we have 3 ray tracing APIs, the Vulkan ray tracing extensions and Microsoft's DXR extensions to DirectX are the kind of the workhorses for the games that have been published recently with ray tracing and for some real-time applications. But we've been working very closely with Autodesk on NVIDIA OptiX and figuring out how to make it be the workhorse for production scale rendering. And so including things like massively complex shaders and complicated scenes and demand loading and other pieces like that. And OptiX is available. There's we support it heavily. But one of the things that we were, simultaneously impressed with and intimidated by was the original design goals that Adrien just told you a little bit about, was that Arnold GPU was going to be feature parity. And that doesn't mean rewrite everything and add all the features to a completely different implementation, but they took a large chunk of the original implementation and we're working to figure out how to make that work on a GPU. Something that was, I think, especially impressive, it challenged, I think, both of our teams quite considerably in figuring out how to do that. But it is what makes it very valuable. So all of the CPU, GPU comparisons that were just shown, I think, kind of speak for themselves. That you can produce the same image, and whatever compromises the 10% of features that are still left to do, I'm sure immediately after SIGGRAPH we'll get back to typing to finish those things off. And so, but as a consequence, it puts a lot of strain on a GPU, where a typical gaming shader will have hundreds of instructions, or we might have millions of instructions. And these are some of the largest, most complicated kernels that we've ever actually run on a GPU. And so one of the things that I think has been especially fruitful is the engagement that we've had with the team and figuring out how to collaborate on features that are necessary for production rendering and that would that aren't necessarily obvious how to do that on a computer that supports 50,000 way parallelism. So demand loaded buffers for large scenes is a huge one. We're making big headway on that. Adrien showed you some highlights of that. handling large shaders and lots of shaders, a lot of different memory reduction optimizations and performance optimization, as well as working on the denoising. And then, of course, testing it and water tightness and things like that give it the robustness that you want to be able to count on from this. So this is what was shown before, but one of the key things is that if you write a renderer on a GPU, you don't want to stop all the 50,000 rays that are being worked on just because you're missing one little bit of texture. And so we've worked with them to build a system whereby we can keep the GPU busy while still loading in data only when it is needed. And so in addition to, there's about a 4x reduction in rendering time on one of these, about a 3x reduction in memory utilization, and about an order of magnitude reduction in the time to first pixel. And so those, that's something that was challenging, but a really good example of where we can, where we've co-designed a lot of the system and figuring out how to make it something better for you in the end. And then the last thing on my list was testing. And so we have now a driver program called the NVIDIA Studio Driver. And so we've worked with renderers like Arnold to ensure that those are tested on our drivers before they are released. It also has some additional features that are useful for creatives, and that is going to be a program that we continue going forward to ensure that you know how to get quality drivers that have been tested against the applications that you care about. And so that's a little bit about the story of where it came from. I guess I just want to say in closing that I've really appreciated the collaboration we've had. It's Adrien and his team have been just amazing to work with. Sharp and friendly and productive and all of the good things that you'd look for in a collaboration. And I think the progress that's been made over the last several months is a really good expression of how that works out. And so a genuine thank you to Adrien, Frederick, and everybody else that supports the project. And we're really excited to see where it can go here and what all of you will do with it. Send us pictures. We'd love to see it. It's what keeps my team going through the ugly bugs and through the hard work and blood, sweat, and tears that it takes to bring us into the future. And that's all I have. Thank you.
We have some microphones in the center aisle. If anyone has questions, we have some time for question and answer.
Yeah, that's a question with it. So, so the question is whether we're planning on implementing caustic. So this would be typically a feature that once it's available on the CPU, it will be available on the GPU as well. So this is nothing specific nothing GPU specific. And caustics is a complicated problem in a unidirectional path tracer. We are definitely doing lots of R&D on complex light transport algorithms. So I can't give you a date, but that's definitely something that we're looking at.
Yep.
Can you have? Do you have any results with the RTX on and RTX off? Can you present some tests of the Arnold GPU, except of denoiser?
So regarding RTX on, RTX off, so your slide regarding the brute force performance speaks for itself, like it's an order of magnitude. On Arnold GPU, since production rendering is 30% ray tracing, 70% shading, of course you won't see like 100x with RTX on, RTX off. You're not going to see that. What you're going to see is basically the time spent ray tracing static mesh go away. So if on your scene, it's going to be scene dependent. So if on your scene you're spending 30% of your time ray tracing static meshes, then you're getting 30%. If you're spending 80% of your time ray tracing static meshes, this goes away as well. And so it really depends on the scene, the type of workflows you're going to see. On a typical production scene, so let's say 30% ray tracing, so those 30% go away. But the RTX GPUs are massive, and they are way better at shading than the previous ones. So it won't be a 30% improvement. You will probably be close to twice as fast.
Twice as fast.
You can't, on a Turing GPU, you can't just turn off RTX. That doesn't work. So the measurements is skewed because you're comparing a new GPU versus an older GPU.
And I guess I'll just reinforce that. So, I talked about a lot of the innovations we've had to invest in the hardware to be better at shading for ray tracing, to be better at the ray tracing itself. All of that rolls up, and if you compare our previous generation, Pascal versus Turing, it's a huge leap. And some of that comes from the ray tracing cores, but it's really the whole package that we think of when we're talking about RTX.
Yeah. I'm just asking because people consider this RT core as like a special core for ray tracing acceleration, so they expect times, but of course it's not times. But the second question is that on the last C graph, it was expectation that by Christmas time it will be some GPU version RTX based. So the 1 year passed. Why it is so slowly? Is it depend on the OptiX version is coming next, or what is the reason of this slowness?
So I'm pretty sure I didn't mention Christmas because I'm not allowed to do that. But yeah, so we presented it first at SIGGRAPH, and then the first actual release of the beta was in March, and it's been available since March, right? And we are careful in adding features not to destroy performance. And some features just take time, and we want to release features that are useful and easy to use and stable. So it just takes time. And the thing is, so let me be super clear, Arnold GPU will be released as a production feature when it's ready. I'm not giving estimates.
And I think the results that you showed earlier, even though it's called beta, it's a very capable system, and I think beta is probably being a little generous, right?
Arnold, the thing is, Arnold GPU is in beta because we don't recommend you to use it in production. You can use it, test it, give feedback. If it's useful for you, it's great. But we don't recommend using it for production just now. And once we recommend it for production, it's when we are really convinced that the level of performance, the level of stability, and the level of features and pixel compatibility is good enough that we can recommend and support it for production. And it will happen, but it will happen when it's ready.
And can you clear the situation with the OptiX version? So it was like old one, now is a 7 coming up. So is it is it pain to switch to the new version of OptiX, or is it the good? So is it slow the process, or is it accelerate the process of issuing new version?
So we have a announcement yesterday of OptiX 7, which is a kind of different API. In parallel, we are supporting OptiX 6 and also announced 6.5. And that's where the demand loading features that we've talked about come into play. And so, to answer your question, is it a pain or is it worth it? Yeah, the answer to both is probably yes. But I think right now, we've jointly made a decision that to keep it and push toward a release with the OptiX 6 series, which is great because it's actually a really good match for what they're trying to do with this full feature parity, and it's I think that strategy has been working out. So.
And the transition to OptiX 7 for us will happen as well, and as a user, hopefully you won't see it.
And you won't see it, and from our perspective, I don't think they need to be in any rush to do it. So.
Okay, thank you.
Yep.
Thank you guys for the talk and making fantastic progress on ray tracing. Just some technical question. Can you talk about on-demand texture loading, maybe in more detail?
Come to the course on Thursday.
On Thursday. All right. Thank you.
So the gist of it is that we have a system that allows you to mark resources as virtual and then you invoke some ray tracing work and mark which resources you need and go get those resources and work on and then go back to ray tracing.
Is it going to be available outside RTX or like the DX pipelines?
Oh, in DX pipelines, all the same building blocks are there in DX, but we have not tried to push it into DX at this point.
All right. Thank you.
Thanks.
Thank you for the presentation. My question is in regards to using it in production, because you recommend not to use it, but if I were to tell my team, go test it, and they're going to try and use it in production, are there specific areas that you think, well, try and stay away from this, or this is known to be sort of not fully compatible yet? I mean, you mentioned, for instance, the VDB implementation.
Yeah, so first in the documentation, we specify everything that is supported, everything that is not working. We try to make it super clear, and if it's not clear, just tell us and we'll improve that. As I said in the presentation, the first thing we started to focus was on a character look dev, like interactive look dev on small to medium assets, because that's the sweet spot for GPUs just right now, given the set of features and constraints and memory and so forth. So look dev, the feature set for look dev should be good. Large volumetric assets, large environments, that's where you're going to run into troubles on a GPU right now in Arnold.
In regards to the volumes, is that because of the shading models are not quite?
The volume is mostly a memory problem. With on-demand loading and by improving our GPU OpenVDB support, we're going to make it better. The actual integration part of the volumetric, the actual integration in shading is already 100% supported and works. Like if you have a volume that is small enough to fit in memory, in a GPU memory, you will have a very, very good match between CPU and GPU.
Sorry, one more. In regards to volume that is small enough, is there a guideline? I mean, I know you mentioned using NVLink to get up to 96 gigabytes of memory shared. Is there a limit? Or?
It's so to get into really technical details, the way we do OpenVDB right now is to use a dense grid. So it really depends on how much your OpenVDB file is sparse or not. If it's really, really sparse, your file is going to be super small, but on disk, but in GPU memory, it's going to be gigantic. And if it's but if it fits the bounding box, if the resolution is relatively uniform, it should work. It's really hard to answer the question for all the volume files out there.
So in regards to the sparse volume set, I know the Bifrost solver is extremely sparse, right? So is that something, I mean, it's not VDB, but is that something that would help with loading that kind of data set into it?
Bifrost volumes on our GPU are currently not supported, but that's definitely something that is actively under development, and of course, we're looking at it. In the future, yeah, it will help.
Thank you.
It's not a huge problem, but I'm just kind of curious why Arnold matte shaders aren't supported by Arnold GPU.
Oh, the shadow matte.
No, just AI matte.
Oh, it's just because I'm lazy. I haven't finished that part. It's really that. Like matte shader. Matte is something that is, so again, we focus on character look there, right?
Right.
And matte involves compositing and more like end production workflows. So we didn't prioritize that. It's not that it's gigantically complicated to implement, although it forces me to wrap my head around matte, which is, I have a hard time with that. But it will happen, and thank you for reminding me.
No, thank you.
Thank you, gentlemen, very much.
Thank you.
Thank you for attending.